what I would like to discuss today is, yes, now it's there. Fantastic. Thank you very much. I would like to talk a bit about what we do in Freiberg, and we have, as I said, the approach of research, but also the approach of transfer. And for this transfer, we utilize a concept called living labs, which you might be familiar with. That means we have the technology at the university and we look for use cases from the public and from SME that can be tried out within the living lab and then be transferred back to the industry to be applied in real life. So if you wish, something like test before invest, or something like developing solutions jointly to real life problems and research activities. Now, the outline you can see here, I'll quickly talk about the background. I already did actually. We'll go into additive manufacturing of bio-based materials and then go further into what we do in our so-called living lab SAMSAX. SAMSAX is the abbreviation for Sustainable Additive Manufacturing in Saxony, because you might know Freiberg is located in the state of Saxony within Germany. And then I go into a bit more details of the technology that you can see here on the left-hand side in the image, actually. This is a technology called binder jetting. And maybe let's start with this image very quickly. You can see there is a powder. This powder basically will be put down and we inject the binder by a 3D printer. Okay, start with the background. Of course, why do we want to do sustainable additive manufacturing? This is actually quite clear. We, of course, are well aware of the facts that we have some climate change. We need to mitigate that. We need to have circular economy approaches to limit the use of fossil materials and so on and so forth. And unfortunately, in additive manufacturing, this is so far not really implemented. You know, many of the materials are either polymers, fossil-based polymers. Some of them are bio-based polymers, like the PLAs, for example. But in industrial 3D printing, you have a lot of metals, polyamides, and, well, not really recyclable or low energy materials. If we can click on the next one, please. We now look into how we can add a benefit through using the new technology group of additive manufacturing to be a contribution to the circular economy approach and the less use of material resources in general. And 3D printing, in contrast to conventional machinings like as milling, for example, has an intrinsic benefit, that is that you only need to apply material there where your product demands it. And also you have, because of this layer by layer approach, very much flexibility in terms of which designs you are actually realizing. That means you can have internal cavities, for example. You can have very intricate structures, small wall thicknesses, complicated things that in conventional machining are either very, very difficult and therefore also cost intensive, or can maybe not even be realized at all. For example, to have an internal hollow cavity inside a solid part. But in additive manufacturing, this is possible. Now then, when we say sustainable, we look at the material and the technology, and we saw that there is a lot of residual materials left over in industry, in agriculture, and so on. And our idea is now to use these materials as a raw material for additive manufacturing. And to do so, we need to really look at all the different angles. So from the material perspective, but also from the machine tool perspective, from the part design and construction perspective, and also, of course, from the properties of the printed parts afterwards. Now, there have been several studies ongoing in previous approaches, and they seem to be quite successful. I'll show you this on the following slides. But what the core challenge is to look at which residue materials are available, ideally locally available, in order to avoid shipping across large distances. And how can these materials, these residue materials, be utilized to create valuable products, to make use of the properties these residue materials have, to integrate them into a valuable product that can then be used again and ideally even recycled afterwards again to start this circle again. Yes, please, next slide. Okay, now you can see here a peach, and the peach is not selected by random. It's because we have been working with a company that produces canned peaches, like the ones that are hugely tasteful. No, I'm just kidding. But these canned peaches are created in a factory, and that means that at this location of the factory, there's a lot of peach stones left over. So they have really, really massive amounts of this, and yet they are not really doing anything of it. They're just burning it. And this was just one example. So our idea is to investigate whether those bio-based residue materials, for example, peach stones, for example, hazelnut shells, straw, whatever, can we use this for something else than just getting energy out of it by burning it? And this is why we came up with this idea. Can we use the new, in quotation marks, technologies of additive manufacturing with these new, in quotation mark, materials, which are actually leftovers, old materials? Please to the next slide. And this is just an overview of some of the things that we already investigated and that seem actually quite nice. And I would really see, you can see that there are a lot of different, let's say, sources of those materials. And there are a lot of different materials that we already tested. So you have a lot of agricultural residue materials from, I don't know, for example, if you look at the kernels, apricot stone, peach stone, plum stone. We have shells, rice husk, for example, coconut husk. We were using in products from Kenya, we were using macadamia nut shells, for example, or maize cobs, which are leftover products there. And we used, for example, also something which I really much like is, for example, invasive species. In Kenya, we were using water hyacinth, which is really a menace there. And this technology incentivized the fishermen to get rid of the plants from the lakes. We can dry them, cut them, and then print with this material in order to get even a motivation to take them away from the sweetwater lakes they pollute. So there's a lot of different things we can try, and we already did. You see that it's a very wide spectrum, and we try to adapt the technology in such a way that it's very much flexible in terms of material input and very intelligent in terms of parameter development. Next slide, please. Okay, so I already explained why we are doing this and what we are doing. So in this case, we're using bio-based materials, ideally something that is renewable and regrowing, and to create available from locally available materials, nice parts. Please click again. And for this, we need to come up with, of course, a screening of materials. You can already click again, please, and develop the technologies to do so. And in this video, you can now see a binder jetting process. You are creating a thin layer of powder, and then you're printing with an inkjet printer, just like your printer at home, on the top layer of this powder bed. But what we're printing is not, let's say, conventional ink to color it, but we are printing like a glue, if you wish, that glues the particles together. Now, depending on the material you're using, we either mix the glue as a solid binder within the powder and just print a solvent. For example, in this particular case you're seeing here, we used a PVA powder material and just printed clear water. We have also been quite actively working with, for example, alginate material as a binder. After the part is printed layer by layer, we have to take it out from the unused powder, as you can see now in the video. And I always tell my students, so if you want to do this, you can also live up to your archaeology skills and ungrab, basically dig out your parts from the restaurant. The good thing is that the material that is not used in the printing is can be used again afterwards, so there's no pollution or any degradation going on, and then you have your part ready. And in this case, what you see in the image, this is packaging made from miscanthus grass and PVA. That means if you put it on the compost, it will be gone in 2 weeks completely. And it's very lightweight. It has similar properties to styrofoam, so polystyrene foam. And of course, if you compare the biodegradability and also the environmental friendliness of polystyrene foam to any other material, you see that's quite bad. So in this case, we can actually make something different. Below, you can see the, let's say, the sourcing. We have the grass on the left-hand side, which is typically grown for a floor coverage for stables and so on. So the plant grows very fast. It's not a competitor to any food plants. It's grown fast and chopped up. And in the chopping process, the very fine particles are filtered out because they're not wanted for the application. And these fine particles you can see in the middle, in the central picture, they are pretty much exactly what we need for additive manufacturing. So we're using, again, only the leftovers of an established process, which not only helps the environment, but it also means that the material is actually quite cheap, which is a very strong difference from the conventional additive manufacturing materials. Now, while this idea is quite nice, we of course have this somehow chicken and egg problem that we have a material and technology without an application because nobody knew about this material and technology. And this brings us to a situation where we're also engineering or developing applications. And now this is where, of course, also this transfer is very, very important to see what we can do. Okay, next slide, please. And again, and this transfer we are doing in the so-called living lab. Sorry, maybe to the previous one. This was the slide with all the pictures in it. And yes, we have this living lab. And for those of you who had the chance to visit us in Freiberg already, you might have seen it. A lab equipped with basically the full process chain, including milling, grinding, crushing, sieving, drying, mixing, printing, yeah, if necessary, post-drying and coating on a reasonable lab scale with a lot of different machines. And this so-called living lab is open to use cases from outside. That means companies, that can also be individuals, that can be agricultural associations and so on. And jointly with them, we look into either their residual material. So we receive a sample and we analyze it and we make suggestions if yes, in what AM technology and which type of properties can be achieved. And then ideally we can team them up with an application or with a company that demands that application. And this is actually also very important, the networking aspect, because the farmers who might produce those residue materials and, for example, the tool makers that might need those printed parts as a packaging, they could even be located next to each other and wouldn't talk to each other, wouldn't know of each other. So this establishing connections and creating new applications and use cases is also a central point of this living lab. Yes, next slide, please. This living lab, for those of you who are who like in definition, the living labs are defined as river platforms, and basically a location where groups can form. Researchers, users, co-develop technologies, test innovative technologies in order to create new products and services. And if that has been proven successful, then the companies can implement this production system, for example, in their own production line. So it's also giving them the opportunity to try new products without having to invest large sums of money. And the first time they can use the technology at university, and then they'll set it up at home, if you wish. Okay, now how are we typically going about this? First of all, we start with a material analysis. That means we collect samples from the industries. This can be agricultural, but it can also be stones. This is probably more interesting to you as the listening crowd here. We have also been using stone material that is created during the cutting of large stone blocks into plates and sheets and so on. So this grinding slurry that is left over, for example, is brought to us. And we do an analysis of it, for example, looking at the powder size distribution, particle sizes. We look at the density. We analyze if it's feasible to be used in additive manufacturing. There's some values, like for example, here you can see the Hausner ratio and the car index. But generally, we assess the material and then suggest what to do with it. And for example, if you now take two different material groups, for example, some, I don't know, textile fibers and some stone grinding slurry, you instantly notice that they have completely different properties. So they also require some different treatment and some different applications. And while the textile ones are very low density, they might entangle very much. They might be quite difficult to print in a binder jetting system with powder. They might be actually quite nicely to print in a paste extrusion system. And it would probably come up as an application somewhere where something needs to be insulated or packaged or dampened. For example, we have been working with acoustic absorbers, 3D printed. The packaging was already shown, but you can also think of something like, for example, pieces of artwork that need to be packed, also pieces of furniture that can be produced like this. Okay, now a lot of different materials have been analyzed. You see in the top left picture our spice cupboard, we call it, where you see small samples of that. But as I said, they are very, very wide ranged and so on. And then, of course, we look into how to treat those parts, how to create products out of those initial materials. Next slide, please. And the companies can, they basically just have to give us a small bit of information, like where does the material come from, which quantities are available, is it toxic or not toxic, and the rest is done by ourselves. Now, generally, we try to keep it circular, and that means we use also our binders, our basic, if you call it glue, that should also, of course, be bio-based and biodegradable. And then we can, of course, also go into recycling of this. And you can see here on the left-hand side, this is a binder from wood rosin, a colifornium-based binder that we developed jointly with the company. But we have also been using starch-based binders or alginate-based binders. PVA, I already mentioned. There's a lot of variety that we can tailor to the application, but also there's a lot of research necessary to continue there. And also, if you see here now in this binder under development, the gelatin, this is also a residue material. You know, when you produce leather, for example, there's a lot of collagen and gelatin left over, and this is giving actually a nice binder, but gelatin is very, very hydrophilic. So as soon as there's any water around it, it will absorb it and will reduce the strength and increase the volume. So we also have to see which application this can be used for. And then, of course, most of the machine tools are not at all made for such a variety of materials. In fact, most of them are limited to very specific, very narrow material property range. And if you now want to use bio-based materials or, let's say, non-specifically created materials, they vary a lot in their properties, even if they are similar. For example, if I was to take the mineral slurry, that is, of course, different depending on which plate, which type of stone has been cut. And if I take the agricultural residue, it's even different from which field they are harvested, even though they might be exactly the same plant species and so on. So what we need to do is make the machine tools capable of working with such deviations. And we do this twofold. First of all, we need to find parameter sets. And our next step for the future, we started already, but there's still a long way to go, is to use integrated sensors, machine learning. If you need a buzzword, you can call it AI, but in fact, it's just machine learning, to analyze the material during the process, like individual on each layer, and adapt the process for each layer accordingly. For example, to increase the number of binder volume or reduce the temperature and so on. So to make sure that the part at the end is the same property, although the input material properties change during the printing. Okay, next slide, please. So you see there's also a lot of course, technology and research and so on development in it. Now, one focus on the binder jetting technology. We have a lot of different printers here. You can see one on the left-hand side. You saw it already in the video. That was the other one. Basically, this is more technical sheet to see that which sizes we can print. And normally they are quite unflexible. So you have to work with what the company intends to do with it. And so, for example, it's not easy to change the ink, which is equal to the binder or the solvent, because the printhead is fixed. And this is something which is, of course, very limiting in terms of research. And this is why we decided to, within this living lab approach that we have here, to come up with a new design of machine tools. And this should be shown now on the next slide, where we have developed jointly with a company from Chemnitz, which is not far from Freiberg, a very open and very flexible binder jetting system. You can see here on the left-hand side some technical drawings. On the next image, we can have a look at the video, at the pictures. But basically, this is now one that is capable of using a lot of different materials, because we can exchange the printheads. We even have more than one, so we can use multi-material. We can, for example, print at one stage water soluble and one stage not water soluble, or we could add some features like, I don't know, electric conductivity or whatever, and we can also print color. But now we have the flexibility to do a lot of different inks that can also be of different viscosity, because we can just exchange the printhead. And because this flexibility is only useful then when we can transfer it to the application, and this means mostly large scale, we have two systems: one small volume system for material testing and parameter development, and the large one that you can actually see here in this top image on the left-hand side, that uses the same technology, but on a very large dimension. So our build volume here is more than 1 cubic meter. We have one of these wooden Euro pellets footprint and then 1.10 meters in height. We can use up to 8 print heads of 4 different inks. So that's actually giving us the opportunity to do industrial scale tests on virtually every material you can think of. Next slide, please. So this is the unit you can see here, and this is the pictures. They are located in our labs in Freiberg. On the left-hand side, or on the bottom picture, left-hand side, you can see the small system, which also has a drop watcher for ink development. And on the right-hand side, you can see the large system, which has more than 1 cubic meter. Right, it's very flexible. We could even print ceramics and stone there. We could even print metals if we want. But at the moment, we are focusing on those residue material upcycling for circular economy approaches. Okay, next slide, please. Yes, some examples. In the central, you see hazelnut shells from, oh, actually, no, this is a peach stone, sorry, peach stone from as we get it until the powder we're using on the right-hand side in those small things. We cut it down, we crush it, we dry it, and of course there we need to see how much energy we put in order to keep it at, let's say, also economically and ecological friendly value. Some applications are packaging and short lifetime goods. On the top, you can see particle sizes, you can see a test part. We also printed with seashells. I don't know why we printed a seashell out of crushed seashells. That's not really useful, but we probably just had this design. The application idea there was to reforestate coral reefs, to have a mobile printing system located on the shore, crush the seashells that are abundantly available there, print something and drop it into the sea immediately jointly with New Zealand. Next to that, you have architectural models, which also have a reasonably short lifetime, depending on how much they are liked or not, even a very, very short lifetime. And you can then reduce the part, reuse the material again to print other parts. This is apricot stone, a leftover from apricot oil production. On the right-hand side, this is part of a stage prop for a theater. And I think if we go to the next slide, there should be even a better picture of this one. Oh no, actually, this is a biodegradation, or showing that it's biodegradable. So this is a PVA hazelnut shell binder, and you can see we put it in water, and so this is not a time lapse, it's just a real-time video. After a few seconds, it starts disintegrating. And of course, that means it's composting very fast, but of course, the application also needs to be somehow useful for this, right? Otherwise, yeah, the application and the biodegradable speed needs to match. Yes, so this is a packaging application. Very quickly, this is printed from paper dust. In fact, this is done at the company that produces those cardboard boxes. And when they cut the cardboard, there is dust created. This dust is filtered out normally in the machine tools. And from this filtered out paper dust, we print the insert for this package. And that is also an economical benefit to the company, because then it is considered as a single material package, which is much easier to recycle and which is less taxed than, for example, a material with a foam insert. Okay, next slide, please. Yes, this is the picture I was mentioning earlier on. We printed 7 of those, 5 or 7, I don't really recall. I think it was 7 of these column tops. And you can see them on the right-hand side. This was in the theater or the opera house in Chemnitz for the AIDA. We printed them from miscanthus grass with PVA, and then of course they were painted by the theater workshop, actually quite nice. And now we have a project where we are using the material created within the theater workshop, so wood dust mostly, to print their own theater stage props, replacing the polystyrene foam they had been using for a long time now. Next slide, please. Mineral prints, and this is something that might be interesting to you as an audience a bit more. We have also had and are currently operating projects in the restoration area where we print mineral materials for applications in, well, in this case, it's just a bust for the museum. It's a tactile bust. It means that the museum visitors are in this case actually encouraged to touch it and to have a feeling of it, also to enable the participation of, for example, visually impaired visitors and so on. And on the right-hand side is just a demo thing. But Next slide, I think, should be a video showcasing what we print with stone mortar, for example, to restore parts of old buildings, of landmarks that have been destroyed. Okay, next slide, please. Oh yeah, now there's one in between. This is also for the museum, where we printed from, I think in this case, again, some agricultural materials, grass materials. We printed the, let's say, the holders for the different exhibits, in this case, minerals, to be ideally fitted there. And yes, so the good thing is 3D printing allows very complex geometry, so you can just 3D scan the part you want to place there, and it's ideally fitting to the next one. Okay, next slide, please. Yes, this is a video now. I hope it's working. Yes, unfortunately the subtitles are in German. I'm apologizing for this. But what we did here, we used a stone mortar to print parts that would then later be used. Our architects wanted to have this like also some sort of texture or some sort of color that is resembling the sandstone quite nicely. So we mixed several colors to do that. Ideally, the best solution would have been that also the grain sizes are resembling the original stone, but this is very, very hard to do within this process. So you cannot really have very small and very coarse particles at the same time. But maybe we get there in the future. And you can see here now how this is created. So again, one layer after the other is put and then printed upon, like you can see here. And everywhere we print the binder in it, in this case, it's just water. Again, it's a restoration water. You just add water and it reacts in such a way as to solidify the particles next to each other here. And then the next one, next layer is put, and the process repeats over and over until the final part is done. The idea is here to have 3D scanned data from heritage site for landmarks. And in this case, this is just a part that you see, this is the same that we did before. But we did this also in real life. I unfortunately don't have a video of it, where we scanned one area of an entrance portal that, and one side of that portal was weathered a lot. So there was a lot of rain having demolished or damaged the area, and while the other side, it was shielded from the rain, was actually quite intact. So we scanned the intact side, worked with the data set, and then printed the other one to be replaced and to be restored. This is something that needs a lot of work to do still, and we are not trying to replace the people who actually do this manually. We just want to assist them in a way that, for example, we could print something that is nearly resembling the final part, and then can have the final touch by the expert in this field, also preserving it accordingly and so on. One benefit of it is that sometimes we do not have access to blocks of stones of the specific quarry anymore, that we would need to replace it. But sometimes in the quarries, there's at least some sand or some piles of particles left over. So we can in fact use the same identical material that was used to where the blocks for the building were cut out centuries ago. We can still use the same material to print replacement parts. But this is again something that needs to be done more in the future. Okay, I think we have only one or two more slides. Yes. So what we do now is, of course, we improve or enhance the material libraries. We want to look at many more materials to see how they behave, what they can be used for. And then, of course, we need to work on the technological side to get the parts more stable and more tailor-made to the application. For example, working with a triggered decomposition that under specific circumstances, the part starts falling apart, whereas they are quite sturdy otherwise. For example, for packaging or furniture, event furniture, short lifetime furniture, this is quite handy. And then, of course, everything needs to be transferred. Otherwise, it will stay in the cupboard, and this is not what I wanted to see it like. So we also work a lot on transfer and industrial scale applications using circular economy principles. And on the next slide, please. I'm inviting all of you to come up with ideas, suggestions, maybe even challenges that we could solve. And of course, all this only works if we collaborate across disciplines. And this is also an invitation and to you all, and maybe even other people to look for joint research and application in this regard, because I think there is a lot of things that are possible. So if I'm not mistaken, the next slide should be the last one. Yes, of course, there's an acknowledgement. The Living Lab has been funded by the state government. And on the very next slide, you can find our contact details. Yes, and I would be very happy to answer your questions, and of course also to welcome you in Freiberg. If you have the chance to pay us a visit, I would be delighted. So thank you very much.